Hello, Math Studies students, and welcome to your online lesson. Today we're going to be talking about systems of linear equations. Our learning intention is that we are going to learn to apply multiple techniques of solving systems of linear equations for equations with two variables, and that should be reviewed. So again, we're applying techniques that we already know to solve these equations, and we'll know we're successful when we can efficiently solve linear equations using either of the system solving techniques discussed in this video. So what is a linear equation? A linear equation is an equation that when graphed forms a line. We won't get too deep into that in this particular video. Perhaps next class we'll talk a little bit more about lines themselves. But though linear equations can have single variables, and they could be graphed to form vertical or horizontal lines, we will mostly be focusing on linear equations with two variables in this particular lesson. Systems of equations, also known as simultaneous equations, or linear systems, is a set of two or more equations that must be true at the same time. And what that means is those lines must pass through the same point. So if we talk graphically, we're talking about lines that intersect. Where do they intersect? Where is there an x and a y value, or two variable values that are true for both equations? So the techniques that we'll focus on to solve linear equations include substitution and elimination. We'll often use substitution when we have a variable by itself, and this is most commonly seen when we have an equation or both equations in slope-intercept form. Though that's not the only way you can use substitution, but again, it's a very common. And then when we have a technique known as elimination, we will be using elimination when we have equations in standard form, or at least have them in some sort of identical form where we can line up our variables and our coefficients and our constants. An equation in slope-intercept form is generally written as the following. Y equals ax plus b. We often hear that sometimes as y equals mx plus b because the a is our slope and the b is our y-intercept. What's great about this is we have one variable, the y, that's already by itself, and that's why it's so great for using with substitution. An equation in standard form, and again, we generally will solve standard form with elimination, though we can always change the form, is written as ax plus by equals c. And there's a few variations on standard form. Despite its name, it's not always standard. Sometimes the c will be on the other side, but generally it's a way of writing an equation where you have this a term, this b, and then your c constant, where they're all whole numbers or integers. We have our variables on the same side for that. All right, so on the next couple slides, we'll actually look at solving using these techniques, and we'll talk about which one might be best in various situations. Now, we can use either of our techniques to solve these, but a very common technique for when we have equations in slope-intercept form is to use substitution. And the reason is I already know what one of my variables is. It tells me right here that y is equal to 4x plus 6. So if I were to say, hey, what does y equal? It equals 4x plus 6. And that's going to be true in both of the equations. So if I go to this second equation here, where I've got my y equaling 2x plus 2, I can take this y and ask myself, hey, what did I already know about y? And I already know that y is equal to 4x plus 6. So I can take this value of y from my first equation and plug it into my y in the second equation, because again, we're trying to find the spot on these lines where the y values would be the same. So I'm going to replace this y right here with the y from my first equation, this 4x plus 6. So I have 4x plus 6, which is replacing y, is now equal to everything that my y in my second equation was equal to, 2x minus 2. So I substituted. I replaced y with the value from the first equation into the y value for the second equation. And now I've got just sort of like a regular algebra problem with a single variable. And I can solve for x, getting x all to one side. So I've already got a 4x on the left side. I'm going to move my other x, the 2x, to that side by subtracting it from both sides. So 2x from both sides. So these x's cancel out, and I have 4x minus 2x, which gives me 2x plus 6 equals, and then there was still this negative 2 here, so I bring that down. Now I'm trying to get my variable all alone, so I'm going to subtract 6 from both sides. I'm running out of room here, so I have 2x These are both negative signs, so I keep the sign and add them together. I'm going to bring that up here. I have 2x equals negative 8. Almost done, and now I'm simply going to divide both sides by 2, and I get x equals negative 4. Now I'm not done yet because I only found out what x is. I got x equals negative 4. In order to find y, I need to take this x value and plug it back in either for this x here or plug it in for this x here. Doesn't matter which one we use. I'm going to use the second one, so I've got y is equal to 2 times x minus 2. Again, that was this equation right here. Now, what is x equal to? I know x equals negative 4, so let's plug that in for where the x used to be in the equation. I end up with y equals negative 8 minus 2, and that simplifies to become y equals negative 10. So my final answer is negative 4, comma, negative 10. And we can write that as an ordered pair. Now that I know that answer, I can actually plug this in to both equations to make sure it's true. So I'm going to leave my answer. But we will try plugging it in to our different equations here. So my x is negative 4, so let's start with this one here. And I've got y being negative 10. And I have 4 times my x, which we know is negative 4, plus 6. So I'm going to bring down the negative 10 on the left side. I have negative 4 times negative 4, which is negative 4 times negative 4, which is negative 16, plus 6. Here the signs are different, negative 16 and 6. So I keep the sign of the larger, which is the negative, and then subtract to get 10. And so I have negative 10 equals negative 10. So it definitely worked for that first equation. And now let's try it out for the second equation. So on this one, I've got y equals 2x minus 2. My y value again is negative 10 equals 2 times my x, which is negative 4, minus 2. So I have negative 10 is equal to negative 8 minus 2. This time the signs are the same, negative 8 and negative 2, so I keep that sign, add them together. Again, it's a true statement. Now, do you need to check your work every single time you do a problem? And the answer is no, unless you want to be sure that you got it right. And so if I was doing a dozen different problems on a homework assignment, I might not check every one of them, but I might check maybe the first one or so. Or especially if I was taking a test and I had extra time, I would check at that point. All right, so that was substitution. Let's move on to a problem now where we do some elimination. So this problem, we have two equations in standard form. In elimination, the idea is as long as our variables are lined up, and you'll notice here we have our x's. You'll notice here we have our x's all lined up. We also have our y's all lined up. And then the constants, or just numbers without variables, are also lined up. And that's a perfect way to solve or set up for solving a system of equations using elimination. But the other thing we want to do is we want to make sure that if we were to add these things vertically, like take this whole equation here and add it to this one, we'd want it so something cancels out. And as I look at it right now, nothing would cancel out. If I added these together, I'd have 2x plus another x, which gives me 3x. I'd have 2y's minus 6y's, which gives me negative 4y's, and then I'd have 5 plus 6, which gives me 11. Nothing's canceling out. So elimination's not immediately working, but we can make a change to this. What we can do is we can multiply by something that will make one of these have a variable cancel out. And again, I don't care about the whole numbers. I'm only worried about the variables. So I'm going to focus on the x's just because it's the first thing here. I had to start with a 2x. So what would cancel out a 2x? Negative 2x. Well, I don't have negative 2x in my second equation. I just have x. But if I multiply everything by negative 2, and I mean everything, I have to distribute it to all three of the terms, I will then end up with something that can cancel that out. So I'll have negative 2x plus 12y. And again, I got that by taking the negative 2 times the negative 6. So negative times a negative gives me a positive. And then finally, negative 12 here at the end. What I'm going to do is I'm going to write my two equations, this original one that I have in the green parentheses, 2x plus 2y equals 5. I'm going to write that over this other equation that I got by distributing the negative 2. So I have negative 2x plus 12y equals negative 12. Now if I add these things together, I will notice that the 2x plus the negative 2x are going to cancel out. If I take the 2y plus the 12y, I end up with 14y. And if I take 5 minus 12, I end up with negative 7. So now I'm going to get my y alone by simply dividing both sides by 14. And I get y equals negative 7 over 14, which reduces down to negative 1/2. All right. So again, I'm still not totally done because I know my y, but not my x. So let's go back to either equation. And I like the original second version because it has x kind of by itself a little bit. If I could just get rid of that pesky 6y or negative 6y. So I'm going to start with that one. So I have x minus 6 times y. Well, what is y? We now know it is negative 1/2. So I'm going to plug that into this equation, equals 6. So I have x now minus negative 6 times negative 1/2. Well, half of 6 is 3, and a negative times a negative becomes a positive. So I'd have x plus 3 equals 6. Subtract 3 from both sides. These cancel out, and x is equal to 3. So our final ordered pair is 3 comma negative 1/2. All right, we're going to look at one more example. And for this one, you'll notice that my first equation is essentially in standard form, while my second one is in slope-intercept form, or y-intercept form. And I have different options that I can do here. I can try to get them both in the same form, or I can just look critically at this problem. So for me, since I see that I already know what y is, and right now none of the variables are really lining up, because in my first equation I've got an x as the first term, down here I've got a y, I'm thinking substitution. Again, because I already know what y is. Y is this stuff right here. So I'm going to go to my first equation, and I'm going to replace y with that stuff. I've got x plus 3y equals 7. Well, again, I ask myself, what is y? It's what we just wrote here in this equation. Y is equal to x plus 5. So I'm replacing the y from the first equation with the y from the second one, and I'm going to use substitution. So I get x plus, and then I'm going to distribute this 3, so I have 3x plus 15 equals 7. Combine my like terms right here, so I end up with 4x plus 15 equals 7. Subtract 15 from both sides. 15's cancel out. I have 4x is equal to negative 8. Moving it up here, I have 4x equals negative 8. Divide both sides by 4. And x is equal to negative 2. Only one of my two variables have been solved so far. I still need y. I love this second equation because y is already essentially by itself. So I'm going to plug in my x value. I have y is equal to x plus 5. Well, what is x? X is negative 2. So I'm plugging in my negative 2 here. And so y is equal to negative 2 plus 5, also known as 5 minus 2, which is 3. So my final ordered pair, x always goes first, comma y, negative 2, comma 3. Now, could I solve this using elimination? So glad you asked. I certainly can. But in order to do that, I would need to reline these things up. And so I've got it in a nice standard form in this first one, but the second one is not in standard form. But I could get it there if I could move the x over to the other side. So what I'm going to do is I'm going to subtract. I'm going to subtract this x from both sides. So I'm going to minus x here, minus x there. And these x's cancel out. I bring down my positive 5, bring down my equal sign, and I have a negative x, and this y here was positive, so I'm going to write plus y. And it's not exactly standard form because I've got a negative on the x, but that's going to work really well for my purposes. So I have this new equation here, just reordered second equation. I'm going to rewrite that as negative x plus y equals 5. And above it, I'm going to write my other equation, which was x plus 3y equals 7. And now we should notice that if I add these things together, these x's will cancel out because I've got a positive x and a negative x, and when you add those together, they cancel. When I add together my 3y and my y, I end up with 4y, and the 7 plus 5 gets me a 12. Divide both sides by 4, and I get y is equal to 3. Now I still need to find my x. I'm liking this first equation because x is almost by itself, so I'll use that one. I've got x plus 3y equals 7. Well, what is y? Equals 3. So x plus 9 equals 7. Subtract 9 from both sides, and I end up with x equaling negative 2. So my final ordered pair is negative 2, comma 3, which is exactly what we got doing it the other way. So the moral of this lesson is use what works. And I mean that as what works for you. Both of these systems work. You can use elimination, you can substitution, and you can really use either of them either time. It's just a matter of what's most effective or efficient so that you can get it done in a correct way and as quickly as you can for like a test or a real life purpose. All right, until next time.